Hi everybody, welcome to the second Turing lecture by Professor J Srinivasan. He's going to talk about this problem on monsoons which is worrying all of us. So we look forward to your talk.
Good morning. Now, today we had two very high-power talks with all kinds of novel ideas. So this will be an anticlimax. There's nothing new here, okay? I'm going to keep it simple. And the concern is to understand what's going to happen to monsoon. And you must remember that when we talk about climate and climate change in India, there's only one focus, that is rainfall. Now, that should be clear to all of you because we live in an area of the world where we get rainfall only about 4 months a year. And we have to manage for the next 8 months. So we have a very unusual problem. Our population is growing and the climate is changing. So water would be the most critical issue. So there's a lot of concern about how monsoon will change. Okay. Now, the point I want to make before going further is, in the last 3 days, you heard lots of talks about complex climate models. They've added all kinds of things in it. Yesterday, you saw how complicated aerosols were with their chemistry, with their sizes, with their distribution, and so on. So one of the concerns I have is, with all that put in and huge number of output, whether it is really improving our understanding of what's going on. Okay, and this is very important, as pointed out by Manabe when he was talking to the media after getting the Nobel Prize. The prediction of climate change without understanding is no better than fortune teller. This is a very profound comment because all of you are going to use all kinds of complex models in your career, and most of them will be black boxes. You won't know all the details of what's going on inside. But unless you understand the phenomena you are trying to model, you might be making predictions which are absolutely useless. So unless you have an understanding of how the model got the result it got, you are in serious trouble. So most, of course, of the students that do research these days are really looking at output of models and trying to figure out why the model is doing what it is doing. To me, it's very surprising that today we have come to a stage where you have very powerful computers, we have great groups which create complex models. The challenge is that the models have become as complex as the real world. Remember that the whole purpose in modeling was to look at the real world, model it to make it understandable. But if the model itself becomes very complicated, you don't know what to do. Okay, but still we have to learn ways to look at the model, try to understand what it is doing. Okay. So how good is our understanding of the variation of monsoon? That is the issue here. And the trouble is, monsoon varies on a variety of time scales, all the way from diurnal variation, which can see from satellite data how every day the variation, all India has a huge diurnal cycle. And then, of course, day to day, then weeks, months, years, decades, centuries, and so on. So all these variations are there, and all of them have been documented, most of them. Now, in order to understand the monsoon, you need a hypothesis as to how the monsoon operates. Okay. The oldest hypothesis was, of course, by Edmund Halley, who discovered the comet, and he thought of it as a giant land sea breeze. Okay, that's how he looked at it. And you must remember that 350 years ago, the major interest was on winds, not rainfall. While those of us who live in India, our concern was on rainfall, not winds. Because that was the time when ships were coming to India from England. So they were very concerned about the direction of winds. And he proposed a model based only on understanding how the wind changes. Okay. Then later, Hadley realized that he didn't include the effect of rotation, which becomes important. Okay. But this is the theory which is still being mentioned in textbooks. All your textbooks, you all read about it, and it is common knowledge, but it is wrong. Okay. And that's the irony that here is a theory, very popular. It's there in every encyclopedia and every this one, but it is wrong. Now, why is it wrong? It's wrong because although it's true that in the month of May and before the onset of the monsoon, land does become hotter than the ocean because it has very little thermal inertia, and the air does rise, okay? But as all of you know from your personal experience, the air doesn't rise much, maybe a kilometer or two at the most. And it forms what they call a heat low in the meteorological jargon, and it doesn't give you rain. It just goes back, and so land sea breeze is not the right model for monsoon, not at all, okay? But it has continued to be popular because no alternative was provided to this thinking, okay? But even 100 years ago, it was criticized by the then director of the meteorology office in UK, and he made a simple point that the average temperature in India is higher in the years of bad monsoon compared to good monsoon. This is common sense. When it doesn't rain, the temperature of land keeps going up. That's obvious. Okay? So as a matter of fact, it's very clear that in years of good monsoon, the land temperature is lower. The years of bad monsoon, land temperature is higher. So the land sea contrast cannot be the driving force of the monsoon. But still people think that it is true. Now, so the point is that the land sea contrast that's occurring after the monsoon onset is a consequence of the monsoon, not the cause. So the cause and the effect has been interchanged, unfortunately. Now, I want to make sure that this is based on reanalysis data, and it shows clearly in the month of July, the peak monsoon month, India is colder than Bay of Bengal, almost same temperature Arabian Sea, which also cools due to winds. So there is no contrast. But here, Africa, there's a huge contrast. African continent, which gets no rain in the Sahara region, has a huge contrast, but there's no monsoon there. Okay. Again, quite clear that it is hot only because it didn't get the monsoon. So the highest contrast is here, but the highest rainfall is here. Okay. And as a matter of fact, if you look along this latitude, the most interesting part is along this latitude, India and parts of Assam get the highest rainfall. Well, here almost there's no rain. Okay. So where there's no contrast, there is rain, and where there is contrast, there is no rain. Now, this was shown even more clearly. That was reanalysis data. You may have a doubt whether it's a good quality data. You can look up the actual measurement of air temperature from 121 stations in India during a 30-year period done by Kotwale and Rupkumar more than 20 years ago. And they showed that whenever, and you look at only this number, June, July, August here, in months of different years, Indian temperature is 1 degree warmer, and in good monsoon years is 1 degree colder. Okay? So quite clearly, monsoon rainfall controls the land sea contrast and not vice versa. So this point, you have learned it in your school, you have to unlearn it. Okay. Now, this misconception continued on. 20 years ago in Scientific American, a very nice article which argued that the rise of the Himalayas may have started the monsoon. This was a misconception among geologists for a long time. Okay? Geologists are very keen to know when exactly Indian plate hit the Asian plate and when the Himalayas rose, because they didn't have proper ways to figure it out. They thought rainfall could be a proxy. When rainfall started increasing rapidly, they thought that's when the Himalayas rose, but that's not true. Okay? So monsoon existed before the Himalayas. The Himalayas are not the cause of the monsoon. Himalayas modulate the monsoon, definitely, no question about that. But they are not the cause. Monsoon exists irrespective of Himalayas. It exists in Africa, there is South America. So you don't need mountains to create monsoon. Of course, the mountains will modulate the monsoon rain. So we need an alternative paradigm.
Sorry,
yes?
Sorry, just for a minute.
Yeah.
Do we have geological data of some sort that says monsoon predate the Himalayas, or you're just saying in general we have?
No, what I was saying is, yes, we have data, as you heard in my first lecture, based on caves and others, how monsoon behaved over the last million years. We have the data, okay? Of course, to understand the impact of India on hitting the Asian plate, you demand data for 50 million years. Some data, they're not that good quality. And what I was trying to say is that today, that's different. I'm talking about when these people proposed it 20 years ago. At that time, they didn't have a good way to understand when Himalaya actually rose. So they thought monsoon could be a good proxy. Okay? But today, there are independent techniques available. Okay, so the landscape contrast theory now can be not only dismissed, can be replaced by an alternative which emerged, but still you'll find out a large number of meteorologists still don't believe in it. This happens in any field. And I don't know how many of you know the history of earth sciences. The plate tectonic theory, when it emerged 30, 40 years ago, it was not accepted by all the older people. All the older professors in universities just didn't like it. But now, of course, everyone agrees with it. It takes time to change people's mindset. Now, today's attitude to monsoon is not as just a rainfall system, but as an east-west oriented cloud band, which in the month of, this is the 1st January, in the month of January, it's in the southern hemisphere, this cloud band, and it shifts slowly as the sun moves north. And this is the manifestation of the monsoon, okay? The intertropical convergence zone, where air from the two tropics meet and rise. Okay? And today we have from satellite data, very nice picture. For example, this is 40th September last year. This is the ITCZ over North India, okay? And this will move down by when you go to October. Yeah, in October it is here. So this is the gradual movement of the intertropical convergence zone following the sun. So main thing which drives the monsoon obviously is the sun and the energy it provides, and that is the driving force for the monsoon.
But is this suggesting it's a very robust kind of a phenomena? Monsoon, because it is governed by sun coming very.
Yes, on a large scale. Let me tell you, the point is that before we had satellite data, our meteorologists had very limited idea what's happening outside the land region. Okay, for example, they thought of monsoon as only land-based system. No, today we know there's higher rainfall in the ocean than over land during the monsoon. Bay of Bengal gets 4 times the rainfall of India, 4 times. Okay? That we didn't know. So now we realize that it's a system which exists both over land and ocean, and it is integrated.
By robustness, I mean that a fear that monsoon might fail is perhaps not such a.
Let me explain. The fear of monsoon failure is partly misconception. As a matter of fact, nobody has even pointed out that Indian monsoon on an all India scale is the most reliable rainfall system in the world. No other system has this reliability, only 10% variance. I mean, for a system which all of you know by now, rainfall is a very, very difficult thing to model and understand, it still managed to come year after year. The problem we're having today is not because of our population. The rainfall got to 10%, we are in trouble. Our economic system can't handle it. But it has been the most reliable system for about a million years. We know it. Data exists for that. Okay, the person who developed, 2 people from GFDL, Neelan was a student at that time, and Professor Isaac Held. As a matter of fact, I want to remind you at this time that Isaac Held has written blogs, very nice blogs. All of you should read them. It's one of the most interesting account of climate and climate change. And he and Neelan Held wrote a very important paper for understanding monsoon. It's called Modeling the Tropical Convergence Zone Based on Moist Static Energy. Okay? It was published almost 30 years ago, and it has not received the kind of citation should have received, because this is a very different way of thinking about the monsoon. Okay, so essentially, they treated monsoon as a heat engine, which it is, that converts sun's energy into vertical motion and rainfall. So that is the key idea there, that it is a way to take the energy from the ocean or land and take it up and produce rainfall. And so their main idea, which is now very, even Tapio Schneider has done a lot of papers on this topic, it is to look at the moist static energy, which is a combination of what we call enthalpy in engineering, gravitational energy, and latent heat. This is the most important parameter. And essentially, when air converges into the zone and it converts vapor into liquid, this quantity is conserved. That is the important part. This quantity is more or less conserved, and the conservation of this quantity is central to this idea of monsoon rain, this one. So here this simple idea that air is converging from both hemispheres goes up and comes out, and to drive the system you need energy. That energy provided by the sun coming from the top, okay, and also from the bottom we can think of energy coming in. But I must tell you that in land this quantity is actually zero, because land has very little thermal storage. So whatever comes in has to go out. So net, this is a net quantity. This is close to zero, but over ocean this quantity is very large. A huge difference. Okay, so this is the difference between these two is the net energy convergence, and that's what is driving this system. So that is the key idea. Okay. Now this is called the energetics framework, and based on conservation of moisture, and water conservation is here, Q specific humidity. This is the mass static energy. Now the original paper of Neil Held did not include this term, horizontal advection. Okay, we found recently that in the Indian region at least that term is very important. Okay? As a matter of fact, this is a vertical integral from surface to the top of the atmosphere. Interestingly, over India, this term goes to zero, which is, if I have time, I will argue why it is so. Okay, so these are the two equations we are going to use together to determine how the rainfall depends on the incoming energy. Okay. Now the same equation that was this again. So it can be rewritten. As a matter of what I have done here, take the equation and divide it one by the other. There's an advantage in this division. If you do that, you get a very simple equation, which is the cornerstone of our argument. Is that rainfall minus evaporation is equal to energy available in the column, net energy available, divided by what we call as the total gross moist stability. Now, Neil and Held called it gross moist stability, but they didn't have these two terms. So their definition did not have these two. They called it GMS. We added a T to it so that they understand we have extended it further. Okay. So what it is saying is that of the energy available, how much can be converted into rainfall minus evaporation? This is a convergence of moisture. Depends on the vertical structure of the atmosphere. This is the vertical. This is totally controlled by dynamics, thermodynamics, and the vertical structure. This is the vertical velocity of the air. Now, why do I like this theory so much? I like it because, in contrast, the land sea contrast theory, which is vague and completely qualitative and wrong, this theory has a prediction which can be tested, which is the cornerstone of any good scientific hypothesis. What it says is, if this quantity is always positive, okay? Well, not always. Also, I'm sorry, not always. Some places it is negative. Mostly it's positive. If this is positive, then the rainfall will be above evaporation. That is the monsoon domain. If this is positive, okay? So that is the prediction. Now let's check that out. Now today we have an advantage that we can measure that quantity luminosity from the top of the atmosphere. Satellite measures it very accurately. So this is the data from Earth Radiant Budget Experiment, and it shows that the net radiation is close to zero or negative over Sahara and Saudi Arabia, and it's positive over India. And that is the main difference between these two regions. The reason why there was no rain over Sahara and there's rain over India is because Sahara is a net energy sink. Sahara is so dry that it loses all its heat to the space, and it is so reflective, the sand in the desert, that most radiation goes back to space. So net available is negative or close to zero. India is somewhat luckier. Most of this region is not desert except here. And so our net is around 60, 70 watts per meter squared. Here it's close to 20 or zero. Okay? That is the key difference. Now, to point out how this goes nicely with the model is that if you plot on top of this net radiation, the actual rainfall in Africa in July, in one example, you see that all the rainfall region is confined to a region where the net radiation is 40 watts per meter square and above. Okay, if you put 1 millimeter per day, you may go even up to 20. So where it is around 10 and negative, there is no rainfall. rainfall is confined to a latitude band where the net radiation is positive and above a certain value. Okay.
So can you explain again why that having net zero prevents rainfall?
Huh?
Can you again explain why the upper region not reflecting all the radiation makes it?
Because the argument here is simple. If the argument in this approach is, if there is no net energy available to bring the air, see, air is a stratified medium, okay? Air won't rise on its own. No, on Earth it won't. So something has to make the air move. I'm not talking about for an hour or two, I'm talking about the whole season. If for the whole season from June to September, you want the air to move upward, you need energy. That energy is provided by the sun. Sun is the ultimate driver. Okay. So what Halley thought was, sun heats the air and air heats the surface. He's okay on that one. But that's not enough. You have to look through the whole process. You have to ask yourself, when the land is cooled by rainfall, it is not so hot. So that is not the only thing. You have to worry about the latent release in the center of the atmosphere. So all that is accounted for implicitly in this model. In the model says that energy is required to get moisture convergence, and how much convergence depends upon the vertical stratification of the atmosphere. So that is a measure of that, an integral of that. Okay. Yes? I can't hear you. Can you? Huh? Next slide. Huh?
Okay, I don't know what to do for that.
Can't hear you. Sorry. Huh?
Deficit region.
Rain is?
Deficit region. Red.
Can you? I can't hear. What's that?
South India is
Huh?
Hello.
South India in this rain.
South India.
It seems a
South India
very
has,
rain deficit region, no?
No. This doesn't rain. This is only radiation budget. This is not showing rain.
Okay.
This is just showing radiation budget top of the atmosphere.
Okay.
This graph I showed for Africa. I'm showing rainfall here in contours, and color is still radiation. Okay. So South India is also part of the monsoon system, although in Tamil Nadu you don't get rainfall in the summer season, but our monsoon starts from Karnataka onwards, Kerala, Karnataka, all the way out.
To get rain because the
Not much rain. Not
the Himalayas and turns back.
No, Tamil Nadu doesn't get much rain in July to September. It gets more in October to December.
Because apparently the monsoon goes, hits the Himalayas and returns.
No, all that is nonsense. All that is descriptive. That is geography. And I'm not talking geography here. Okay, that is descriptive account of what's happening. They say the monsoon rain goes up. That argument is wrong. Okay. For example, the word northeast and southwest is based on wind direction. Okay, but that is not the way the rain. You must remember that the northeast and south monsoon was set because the sailors were coming and they looked at the wind direction. But that's not the way rain system moves. Rain system moves in a more complicated way. Okay. Yeah, this I get repeat of that. I think I'll have to skip it. This is the same thing. Okay. Now, to point out that when models were modeling African rainfall, I looked at that in some detail, and you find that this is observed radiation in the month of July. And this is what UK Met Office simulated, and this is what the German MPI, Max Planck Institute, did. You can see that both these are wrong compared to this. Okay, this is somewhat closer. So the UK Met Office had too low negative net radiation. So their rainfall system moved further south. So this was the point that many of them had problem in simulating African rainfall because they are not able to get the radiation budget right. So that is one of the diagnostics that comes out of this model, that if you get your radiation budget wrong, your monsoon won't be right. Because for a long time, many centers who developed climate models had difficulty getting monsoon right over India or Africa. They did not look at the possibility that the radiation part of the model was wrong. Now, I developed a diagnostic model based on this equation, and I showed that in one of the models developed by NCAR, this is NCAR model, the error between observed rainfall and simulated rainfall and observed rainfall, that is the difference, depends upon the error between net radiation in the model minus observation, and the largest error was in NCAR at that time. This is about 20 years earlier. Okay, so I was able to use this model as a diagnostics. By the way, this model is not a prognostic model. You cannot predict rainfall. Given all the data, it can tell you why it's happening. So it's more for understanding, not for prediction. So let me put down that model in a more descriptive way here. So in this model, rainfall equals evaporation, and so and the difference is what we really are interested in. Depends on incoming radiation at the top of the atmosphere, 1 minus what is reflected here. Okay, this depends on clouds, ice, and aerosol, all of them, and outgoing long-wave radiation, which also depends on clouds, carbon dioxide, water vapor, carbon dioxide, aerosol. Okay, so this is a part you have to simulate correctly, and many of the models have difficulty because of the way they represented clouds or aerosols, and the denominator, of course, is the vertical structure of the atmosphere. Okay, now note that if all these quantities E, S, alpha, Ola do not vary much, then P is proportional to S. Okay, keep that in mind because I'll come back to that when I talk about paleoclimate. Okay? So if all the other things didn't vary, rainfall should proportional to incoming radiation. Now, this is repeated. Okay, I added one more. Okay, this quantity I showed under certain simplifications can be written as a constant which depends on the vertical profile of the winds and so on, and the total water vapor in the column. Okay, so this was a further extension of linear held model, and so this shows the important role played by water vapor. Okay? When I first wrote this paper, the referee rejected the paper on only one count. He said this has a singularity. When this equals this, it blows up. Right? I also mentioned that I know it. As a matter of fact, I showed that in the various models I looked at, NCAR and Japanese and so on, whichever model had a constant C, which was not right, and made this quantity go close to this, that model tended to have too much rainfall. So this model actually gives you insight. But it is true, the model has singularity, and that singularity is partly because in the original linear held model, they neglected the horizontal term. Now I included that. At that time, I didn't include it, and so the singularity. But the singularity is realistic, and those models which for some reason don't get this number correctly when compared to observation will give either too high or too low rainfall because of this singularity. Okay, so remember that you can write it in this model. If you want, you can rewrite it that P watt by C minus P watt, that form, and later on you will see that observations show that when you plot rainfall with water vapor, it has a very nonlinear behavior. Okay, and I'll come to that later. Okay, yeah, right now it is that. This is the measurement in Dillon in West Pacific, only measurement I know of. This is hourly data. Okay, so he is comparing rainfall, hourly rainfall on the y-axis, and the amount of water vapor in the column, which is my P watt in this case, x-axis, measured. And here he has looked at water vapor 3 hours earlier with rainfall at the present time. Okay, because he wanted to show that higher water vapor 3 hours earlier is a prerequisite for high rainfall. This is a very nice result showing that water vapor increase is a prerequisite before rainfall can occur. That's obvious, of course, not surprising. But later on, he also showed that after rainfall occurs, the water vapor goes up further. Okay, so this is a paper published around 10 years back, and so shows the important role played by column water vapor on rainfall, and the thing is nonlinear. I want to realize how nonlinear it is. It's very sharp. As you go above 70 and 75, it really goes almost exponentially, and that is reproduced by this model. Okay. Now, I also use a model to look at the seasonal cycle of rainfall. It does not do perfectly, after all, it's a simple model, But by and large, all the parts of the world, India, South Africa, North Africa, and South America, South Africa is here, I'm sorry. All the regions, monsoon regions of the world, it gets the thing right. But of course, there are departures here and there, because I used data at that time, 20 years ago, of reanalysis, which quality of water vapor data was not that good.
Question.
Okay.
Question.
Yeah. Yes.
The previous plot, the previous one.
Yeah.
So, above, let's say 70, the column water vapor, if it increases, is there like a critical number above which it can never be observed?
That is R is 100%. Once you reach R is 100%, that is the upper limit.
Right.
Yeah.
Right.
As a matter of fact, some people plot it as a column relative humidity. Yeah. If you go beyond 100, you can't go beyond 100, right? That is the limit.
Right.
Thermodynamics.
But it looks as if there's a critical number well below 100, like
Yeah, so according to, if you believe this model of mine, this model says P watt cannot exceed C. Okay, that's why the referee didn't like it. I said that cannot exceed C, but I also admitted that this will change if I add a few more terms in the equation. But this shows clearly there is an upper limit of P watt, and that comes from thermodynamics essentially.
Can you say once more what C was?
Sorry, I skipped that because I thought there's enough time. C comes from this equation. In this, what I did was I skipped all those parts. Initially I neglected these two terms. I assumed a profile of omega and m and q, and while doing that, I got this to be equal to C by P watt. Okay, so you can do it analytically almost. Okay, but I didn't want to spend too much time on it because today we know that we cannot neglect those two terms. So that I'll talk about when I look at paleoclimate. Yeah, so to me, this is the right diagnostic model to understand monsoon behavior, both in a model and in observation. Okay. Now, let me say a few words about how monsoon is predicted in the present day. That was just a model. So daily weather prediction, of course, depends on the initial value problem. Today, we are doing extremely well in daily weather prediction for a few days. But the problem of interest to many of us is seasonal or longer prediction. Okay, that's the boundary value problem. That has turned out to be very hard. It has not yet really been solved clearly. Okay. Now, the advantage in the initial value problem is you have good data assimilation, which is the fusion of observation and forecast to obtain the true state of the system. Now, I don't know, maybe many people here may not know about it. This is a peculiar term used only in meteorology, because in meteorology, we don't get observation everywhere. There are always data gaps. So we use the model, latest model output to interpolate cleverly. Okay? Instead of just doing linear interpolation, something, you use a model as a, wherever data is missing from the observation, model is used as a substitute. Okay, and this turned out to be quite good, except over remote oceans, maybe it's not good, but otherwise it's a very good way to get the true state of the system when you don't have enough data. Okay. Now today we are lucky because we have satellite data. Huge amount of satellite data goes into all these models. So you can see in this period of 15 years, it has just gone up rapidly. Okay, and so data, millions of units of data assumed per day. So this is what has helped. If any of you have followed, although there's a cartoon showing how poor our forecast is, the fact of the matter is 2 to 3 day forecast today by all weather forecasting institutions all over the world, including India, are very good only because even though the model has lots of problem biases, you initialize the model with the observation, then the model will behave correctly for a few days. Then the model will drift towards its own climate. Every model has its own climate, which is different from the observation. Because of all the problems that Saravanan and Krishna and others mentioned in the last 2 days, due to parameterization, there are lots of problems in the model. The model wants to drift to its own climate, but if you feed it the right initial condition, where the cloud is, where the rain is, it will behave correctly for a few days. And that is about 4 or 5 days right now. Now, let me go back to a little bit of history in India. In India, monsoon forecasting was started by Sir Gilbert Walker, who was the director of India Met Department for 20 years. He was a mathematician. And it's remarkable that at that time, we had no satellites, we had very few observations, and based on just surface pressure data around the world, he proposed many pressure oscillations all over the world. Southern oscillation, which is very important today, we know that in the Pacific Ocean, North Atlantic oscillation, not all these he proposed just based on a few data points around the world. But at that time, unfortunately, he did not have enough data on surface temperature of the ocean, because all the data that was available there were a few ships of opportunity, not real observation. So he could not connect these oscillations to what's happening over the ocean. That came much, much later. But he proposed a way of forecasting monsoon based on oscillation of surface pressure between Darwin and Tahiti. And this was a remarkable proposal. Only thing he didn't know is connected to what's happening in the ocean. Now we know today that what is called southern oscillation is related to a phenomenon called El Nino in the Pacific Ocean. And the two are coupled. It's a coupled system. And today, because of a huge number of observations and model, we are able to predict the El Nino at least 6 months in advance, which is a remarkable progress in this field over the last 30 years. Yeah, so this is the example of what is the state of the ocean last September. We had a large, cool ocean here, which had impact, some impact on the monsoon. And so this we are able to predict today at least 6 months in advance, the state of the ocean. So this is the region of great interest to everyone, because the warming of the ocean, this equatorial Pacific, has a huge impact not only over India, it's over Indonesia and other parts of the world, because air rising here sinks all over the world and determines what happens to the weather in other parts of the world. So here an example of how one location which is very, very popular, this region called Nino 3.4, between 150 to 120 Western Pacific equator, how the temperature has fluctuated over the last 40 years here. And you can see every 4 years or so, you get a warm episode, then a cold episode follows that. Okay? So this has impact on the monsoon. So about 50% of the droughts that we had over the last 150 years is due to El Nino condition. But irony is, although El Nino can be predicted 6 months in advance, not every El Nino causes a drought. So that was discovered later. So some of the forecasts went wrong. They were assuming El Nino will definitely cause a rain. Then people realized that other oceans also play a role, not just the Pacific Ocean. So, but if other oceans are not having any anomalies, then warming of this will definitely cause a drought over India and definitely over Indonesia. Okay. Now, today we know that not only Pacific Ocean, the Indian Ocean and also have an impact on the monsoon. And it's somewhat more complicated. Pacific Ocean affects the Indian monsoon, and Indian monsoon also affects the Pacific Ocean. It's a two-way process. Same here. Here we don't know. So these two are complicated because this is because Indian Ocean is so close to India that whatever happens to the Indian monsoon affects Indian Ocean immediately. Okay? This is a little far away, but still you'll find out that if you have a good monsoon this year, it will affect the Pacific Ocean temperature in the month of October, November, December. So it's a two-way process, interacting system. And in the last 20 years, it was discovered that a similar thing occurs over the Indian Ocean also. Like El Nino, there is a warming here and cooling here and vice versa. This also affects. But this one is more complicated because this ocean is small. It's not a big ocean. And so what is happening here is closely coupled to what's happening here. So this cannot be really used for predicting that, because they are working very closely together. Okay? And this how this Indian Ocean dipole, whenever it's warm here, it rains a lot here, and it affects the Indian monsoon. But if it's warm on the western side, India benefits by the higher water vapor over the Arabian Sea. Okay, so you can see the example here given here. Years when only El Nino was there, Indian monsoon was below the normal. Normal is shown somewhere. Sorry, it's anomaly. So normal is 0 here. So what it shows here is that over this part of India, not whole India, the anomalies can be as high as 400 millimeters, but not all years. You can see that there are years when rainfall was even above normal here. And the amount of departure also is highly variable. Okay, but if the El Nino combined with positive Indian Ocean dipole, that is this part of Arabian Sea is warm, then this compensates for this, then you get almost normal rainfall. That happened in 1997. 1997 had the most powerful El Nino of the last 100 years, but it had no impact on Indian monsoon. A great surprise. Then it was discovered that it is this, this anomaly here affected. Then if you have only positive IOD and no El Nino, of course it will go above. So these two have to be looked at together.
Sir, just a second. I'm
Yes.
sorry. What are those boxes for?
Huh?
What are those boxes for?
These boxes? Oh, this is standard statistical. This is mean and departure, one sigma, I think. That's what they are showing. What is the mean, what is 1 sigma? Okay, standard statistical plot.
Sorry.
Yes.
Srinivasan,
Yeah.
you may come to this, but in terms of the basic model you proposed,
Yeah.
is working so well.
Yeah, that model is a diagnostic. That model will not help me to predict any of this. It's a diagnostic, that's all.
But still, since it works so well, the ocean effects, El Nino, etc., where would it go in that model? In the
It's very simple. In my model, all El Nino or IOD is to increase water vapor here. See, remember that water vapor to India comes from Arabian Sea, nowhere else. See, India is a very interesting place. The winds move from the west, so all the water comes here, but the systems are born here. The systems come from here, but they converge the water vapor from here. That's the interesting point. Okay. The systems are born in Bay of Bengal and they move. This way, all of you have seen satellite picture showing depressions moving across. The systems are born in Bay of Bengal, but the rainfall water vapor source is this. In my model, this is the key location. Okay, now from the time of Sir Gilbert Walker to about 10-15 years back, the India Met Department only used statistical methods. Okay, yeah.
So if the water vapor, if you're not dependent on Bay of Bengal for the water vapor,
Because wind is blowing from the west.
yeah. So when we're talking about, the mixed layer thickness of the Bay of Bengal and all, that's only because that will affect the systems.
Depression formation, yeah. See, the temperature of the Bay of Bengal will decide whether depressions will form there or not. It has to be sufficiently high, about 28, which Ceylon's not discovered. So that depends on the Bay of Bengal. But once the depression forms and moves into India, it can converge moisture. That moisture comes from Arabian Sea.
Excuse me.
Yeah.
Hi, I'm online. So according to your model, if the net energy is positive, there will be an updraft.
Online. I can't hear, please. My hearing is not. Somebody can repeat that?
Hi, am I audible now?
Not clearly. Somebody can just repeat it for me.
So I'm asking, yeah, so all I'm asking is like, you're saying that if the net is 0, then there would be an updraft. Does your model tell us till what height would that updraft be of the this moisture or whatever?
Let me explain to you. The diagnostic model is not looking at updraft. Diagnostic model is not predicting updraft. Diagnostic model really saying, you must remember that during the height of the monsoon, let's say July, okay, air has enough moisture to carry it up to 5 kilometers. It'll keep going up, no problem. So the point about this is how much of the energy that's converging in the lower layer, how much it goes out, okay? Because remember, let me go back to that argument so that you understand that clearly. I get the graphics here. Yeah, the key point here is that the value of m here is lower than value of m here. So more static energy is being brought in by converging air. It goes up and it goes out. This quantity is more than this quantity, okay? Because that's the shape of the more static energy profile that is given. Okay. Therefore, this system can, remember, I'm talking about a steady state model. I'm not talking about transients or how it starts. That's not the diagnostic. So this can continue to exist in steady state provided enough energy is supplied to take care of this energy export.
Okay, it's not talking at all about the height of these columns and so on. It's
This
just saying there would be an updraft.
This one is saying, given that monsoon is there, it will continue to be there provided the energy required to export the mass static energy, this quantity is more than this quantity, M going out, you get an M coming in. So you have to supply that much energy. If you don't supply, the thing will come to a stop.
So the reason I'm asking this is like the traditional definitions of ITCC. There is a convergence, but the updraft is still, let's say, 700.
No, you're looking at two smaller scale. Let me explain. This is a diagnostic model. It doesn't look at a parcel lifting up. That is not the point. This is just an energy and moisture balance model.
Sure.
Remember that I'm not, this model has not come from looking at a parcel theory approach. It's not that. I'm assuming you know the vertical profile of mass static energy. I'm assuming you know the vertical profile of vertical velocity. All that is given. Given that, I'm saying that if the air going out as high mass going in, then you need to supply energy. That's all I'm saying.
Got it. Okay. Thank you.
Okay, this is not a model which goes into details of parcel theory. That is a different approach. Yeah, so what I was pointing out here was that Walker realized the connection between the Pacific and the India, but he was not able to see the connection, sea surface temperature. Today we know that, although we know it, we are not able to still accurately predict droughts in India because not every El Nino causes a drought. And not only that, it also depends on where the warming is. If the warming occurs here, the coast of Peru, we don't get a serious drought. If the warming occurs over Central Pacific, it causes a more serious drought. Okay? That's partly question of there's air rising, where does it descend? If it descends over India, then we are in trouble. If it descends over Indonesia, we are not worried. And that is still not fully understood. What are the things which control that? Okay. Yeah, so what I said was, from the time of Walker till about 10 years back, India Metropolitan relied only on statistical forecasting using various parameters like sea surface temperature over the Pacific and temperature over Himalayas and so on. And they kept predicting. And so this is the first forecast that they make in March or April. That's the red line. And actual rainfall is in blue. Clearly showing that regression method is not good for predicting extremes. Okay, it predicts something, but nothing. So the point is that they continue to use this model, this kind of regression method, because at that time we had no other method available. And the fact of the matter is, they got it right some of the time because in any 10-year period, India used to have one drought year and one flood year. 8 years were normal. So you don't require any regression method. You don't require anything. I just say monsoon is normal. I'm right 80% of the time. Okay. This was not appreciated by many people. They kept saying you're doing well. But the main purpose of prediction was these extremes. Okay. That it failed totally. Okay, a little bit success, but so the point was regression method is inappropriate. And today Balaji also made the point very clearly. If you want to get extremes right, you have to do something more sophisticated than regression. Now, today we are doing both statistical and dynamical based on the model that Krishnan talked about. But even then, things are not that good. For example, I looked at the last 10 years of forecasting of the seasonal mean rainfall. Here, the red is statistical, green is dynamical, and blue is actual. Okay. Now, we'll start with 2011. I would say dynamical did not bad, but statistical got it wrong. 2012, dynamical was wrong, and so on. And only in some year, like El Nino year, both were right. Okay, there is a strong El Nino, and then anything happening in Indian Ocean, it gets it right. And in this year, both got it wrong. So generally, I would say at this stage, as of last year, neither statistical nor dynamical is doing well. Okay, not surprising, as many of you already have heard, because of the way we parameterize clouds and rainfall, which is very, very empirical and not based on real good observations or understanding. You can't expect success in predicting seasonal mean rainfall. Okay. Now, in the last 30 years, a lot of work has been done with atmospheric model and coupled models. Many of you have heard a lot about it, but I'll show some of the results here. Now, I'm just here showing from a paper published by Trivedi from IITM what is observed rainfall over India, this one, and what the observed variability, year-to-year variability. Okay, and these are the various models, and the small dots are each run of an ensemble, and the big dot is an average. Okay, and you can see is that in most of the cases they are nowhere near mean observed and mean variability. That is, no model is able to correct either the mean rainfall right or the variability right. That is the state today of the modeling effort.
Sorry, Professor Srinivasan.
Huh?
The actual data is the green dots?
This is actual data, mean and variability.
Oh, I see.
Nobody is coming near it. No one is near it. That's the whole point. Can you imagine, Meteor France? I mean, it's really such a low rainfall compared to observation, and this is very poor. I would say among them, I would say UK Met Office, no, this UK Met also is very low rainfall. So this problem is there among almost most of the models. They are too dry most of the time. One more example from a paper by Jana Azad and Rajivan published in Journal of Climate. You can see that most of the models are too dry. Okay, observation is here. Okay, this is the variability, the dotted line. Most models tend to be too dry, and that's a serious matter. Not fully understood why models are not able to get that right. This is an example of interannual variation. Black is observation, various models, huge number here. And you can see that except for 1 year, 1988, which was a La Nina year, when precipitation was cold, all of them got it right. Okay, but in all the other years, there is no, and look at this side, everybody got it wrong. Okay, that's to me a serious matter. That means something is wrong in all of them. You can't blame any one model for it. Now here is a comparison, not the latest one, but the last comparison. Black is the observation, green is observation, IMD. Black is the ensemble mean, which is well below the observation. And you can see large number of models, each model separately shown here, are well below the observation. They are too dry, this one. So what I think in this Rajivan has done here is, he considers those in the green bunch are, green is part of variability here. So those who are somewhere here are okay, but these are terrible. Okay. Now I looked at one of these models some time back, and the coupled model, that is the ocean atmosphere coupled model, did quite well the seasonal cycle. I was quite impressed. Okay, black is the observation, and red is observation, black is the coupled model. You may not think it's very good, but it's not bad. But when I ran the same model with specified sea surface temperature, the atmospheric model, it's rained too much. Now that puzzled us, and we asked why. It turned out the model had two errors. One was its cumulus scheme tended to rain too much. But when you put in a coupled mode, the ocean was too cold. The two cancelled out. So remember, just because the coupled model got the right answer, it may get the right answer for the wrong reason. Okay, so one has to be very, very watchful. Look at each part of it, because this was just a fluke. It happened to have two errors which cancelled each other out. Now today things are improving. Here is a comparison of June, July, August rainfall made by NICAM, a Japanese, this one. Look at the resolution, 7 kilometers. Okay, this is where everybody is heading. We are at already, yesterday Pandora Krishnan, they run a 12 kilometers model for forecasting, not for climate. And this shows great promise, because this is the observation from TRIM, this is the model, and I am truly impressed. They get, of course, Western Ghats right because they have the right resolution, and they are able to get the Burmese rainfall correct. So I would say that the future lies in going to higher resolution, and that will take care of most of the problem related to the cumulus scheme. But aerosol, it won't take care of. Aerosol is going to be a nightmare for a long time because aerosols have the following problem. They are highly variable in space and time. We don't have sufficient observation, and the chemistry of the aerosol is very complex. That's because you know what, the total aerosol means nothing. If it's black carbon, it will do something. If it is sulfate, something else. So aerosol is going to continue to haunt us for a long time. And worst problem is, we in India get a lot of dust in this region. Okay, notice that the model is slightly off here. It was a little bit more into rainfall into Pakistan than the observation. That's because the model does not handle dust. Unless you get the dust correctly, its concentration, its properties, you will not be able to succeed. Yeah.
The white region.
I can't hear. Somebody has to repeat. I can't hear you.
What are those white regions?
Huh?
What are those white regions?
No rain. No rain.
No rain.
Yeah.
Okay.
Or below 2 millimeters per day. I'm sorry. Below 2 millimeters per day, which is as good as no rain. Okay. So this is a region below 2 millimeters. That is not correctly, that boundary is not correctly reproduced.
This left is the actual, right is the forecast.
Yeah.
When was the forecast made?
This was a 3-month forecast only, 2004, based on May conditions. Something.
How significant
Huh?
how significant are aerosols in affecting the rain? 10%?
You can see that here it is not affecting so much, but except at the border. See, Pakistan has a lot of aerosol being a dusty desert region. So this interface is going to be a problem. But here, see, the point is once monsoons start, aerosols are removed, it's a clean. Okay. Aerosols is important in the month of May and June. Once all the rainfall occurs, completely it cleans up. You can in Delhi, you will see. Totally it goes away.
So just to get a feel for it. So suppose in April, May, we have a lot of pollution, lot of air.
Yeah.
How will that affect the monsoon?
Onset phase, when the monsoon onset occurs. See, the point is that in the month of late May and June is the critical month of the onset of the monsoon. If there's a lot of dust hitting the atmosphere, it will alter the way the onset occurs. Yeah. Yeah. But once the onset occurs, the monsoon takes over, everything else is secondary.
So, just to ask you,
Huh.
the aerosol, how much error will it cause both the uncertainties we have? Vis-a-vis the onset and after the onset?
I don't know, you must ask either Chandra or Liu about that. I have not seen a paper showing how dust impacts the onset. I have not seen a paper. There may be one because the territory is very vast, but you have to find out from them whether anyone had looked. I think there may be 1 or 2 papers on ever dust on onset. Okay. So I would argue qualitatively, if there is dust, a lot of dust, it will actually promote onset. Because dust warms the atmosphere, so it will promote the onset in my view. Okay. So, but I have not seen actual simulation comparing dust, no dust. I have not seen. Unless, have you seen any? Yeah, dust is not modeled at all, right? Am I right? NCAR does not have dust in it.
You see the brown cloud.
Yeah, but dust is the most important. As a matter of fact, dust is more important than anthropogenic aerosol in the month of May, because the huge winds from Pakistan, Rajasthan, Saudi Arabia, they kick up dust. All of us know that. But that's not modeled.
I'm sorry to slow you down, but I mean, as an outsider, this looks so promising. So you mean if we have a 7-kilometer grid?
Yeah, we'll do forecast. We'll do forecast very well. And this one is, of course, 3-month mean. But I can tell you, this is the misleading part. This is that one realization. They may do badly in 2015. I mean, you have to be careful. This is one sample. Okay. So they were lucky, maybe. So we have to see. I would have liked to see an ensemble mean, many simulation. But I'm showing you only because of this spatial structure. Very impressive. That's because orography, I'll come to it later because we have looked at that I'll come to that later.
I have a probably dumb question.
Huh?
I have a probably dumb question.
Yeah.
Every time we hear that when the atmosphere warms, it's more likely to rain. But then when the atmosphere...
But that is a wrong statement, in my opinion. When there is more moisture,
Right.
rain. Yeah. But I can tell you why. The moisture warms only after the monsoon onset, really. See, after monsoon onset, the air rises and releases heat at that level of 5 kilometers. Okay. So to me, the heating of the entire atmosphere is a consequence of the monsoon, not the cause.
But then moisture also, I mean, relative moisture is more important, right? Only when relative moisture goes above a certain amount, you can think.
There's a
Because
threshold
otherwise, if
value.
it's warms, it's just more water in the atmosphere.
It's above certain threshold value. Yeah. If you look at the graph of how P went varied like that, you have to be above threshold for you to rain. Yeah. One more example I want to give. Not this is in Europe, not over Himalaya. You can see that this is a 12-kilometer ensemble mean. So this is now more realistic, not one simulation. It is very poor, but you go 3 kilometers, they are able to capture the observation. This is a recent paper. So even in Alpine region, resolution is very critical wherever there are mountains. No question about that. Now that has been highlighted here by, I'm going to compare now a 20-kilometer model, Japanese model, which one of my students went to Japan and looked at it. This is the orography of that compared to observed orography from satellite data. So it's quite close. But if you run a model at 300 or 200, you're going to have a problem, okay? Especially getting the Western Ghats correctly, you have to get at least to 50 kilometers. In this is not there, in this little bit is there. So India has a problem. Not only we are in a complex region, we have two orography, the Himalayan orography and the Western Ghats. If you don't get that right, nothing will come out right. Okay, so now I'm comparing a simulation by the Japanese model made by one of my students. And he compared the observation over a 10-year period with a model simulation over a 10-year period. And this is atmospheric model, I believe. And I would say this is very good, okay? But there are some mistakes you can see somewhere here, or West Bengal, that is very poor. Kashmir is very poor. But otherwise, this model structure looks to me quite impressive. Now, I want to do a close-up of Kerala, which has a lot of orographic rain. I would say this is pretty impressive. The gradient of rainfall as observed and as simulated, okay? So that clearly shows 20 kilometers is the minimum requirement for you to get your gradient right. And this is northeast monsoon. That also is done quite well by this model. And this is about climate change. Okay, I will not show too many things with climate change because I think our ability to predict climate change, monsoon is very tough. But this model says that over most of India, in the future, rain will be more by about 1 to 2 millimeters, but over Kerala, it will be less, okay? Now, this is remarkable prediction because if you look at data from Kerala over the last 50 years, rainfall has declined. So already climate change is seeing its effect in Kerala, but you don't hear that much of media coverage because Kerala has such a heavy rain that a slight decline is not seen. But locals tell you it is not raining as much as used. Now, this is very interesting result because we looked at it in detail. This is because the jet which comes from here, the Somali jet comes from Somali region and turns here, it moves north slightly during global warming. And that shifts the rain band to the north. That's the main reason. And now I'll come to the other important prediction for the future based on my simple model. If we look at rainfall and water vapor, I've shown here for the European model, the blue, this color blue is the present and red is the future. Now, this is a very important graph because it shows clearly that for the same amount of water vapor, in the future, you will have less rain than the present. Okay, that's a key important point. But fortunately, water vapor will go up due to global warming. That is guaranteed. When the sea surface temperature goes up, more moisture comes out of the ocean, that will happen. But depends on how much. If it doesn't increase much, then we will get, for example, right now at 50, you'll get only 4 millimeters while we are getting 6 millimeters. For you to get 6, you have to go up to 65. So that is the problem. So if you ask me, will monsoon rainfall increase over India? The answer is we don't know. Thermodynamically, yes. But if dynamically there is some change and enough water vapor is not there in the column, then rainfall will go down. Okay. But most models are predicting higher rainfall due to thermodynamic effect. But we know that dynamics is equally important. Okay. Huh? No, whatever goes, rainfall goes up. No, whatever goes up, rainfall goes up. Because if you want a simple argument, no, let me explain. All I'm saying is in both curves, as whatever goes up, rainfall goes up. All I'm saying is for the same amount of water vapor, rain is less here than here. For the same amount of water vapor, in the future, rain will less than present because the vertical stratification is different in the future than present. For the same amount of water vapor, compare for same water vapor, we get less rain. But in future, water vapor will be more because of thermodynamic argument. Temperature goes up, water vapor goes up. Okay, 7% per unit degree centigrade. So this is a very important graph which clearly explains why it is so difficult to predict the rainfall goes up or goes down. As a matter of fact, 10 years ago, models were half the models said more, half said less. But right now, most models are saying it's going to increase. Yeah.
Thank you. Can you go to the previous slide, please?
Huh?
So, like, what is the definition of future here? Like, what is the definition of future?
Future is
like
last 10 years of the 20th century, 21st century. Okay.
I see. And
2090 to 2100. That's the standard. I'm comparing 10 years with 10 years. Okay.
And this is purely based on temperature, or is it other factors also? So
what is based on temperature? Now I'm comparing what, for example, in this case, if I remember correctly, I'm comparing 1990 to 2000 with 2090 to 2100. Two 10-year periods.
Yes, but like under what scenario of anthropogenic emissions and temperature rise?
This was the old one. This would be what is it called? RCP 8.5. That kind of scenario. Okay. The highest scenario. See, let me be very frank. Because models have lots of problems, we always take the highest scenario because we want a good signal. I will not take a low scenario because there will not be enough signal. So everyone always shows you the one with the highest amount of CO2 emission, so that I get a large difference. I mean, that's you can't help it.
Thanks.
Yeah. Yeah, I know. No, actually, I have to go after this. So I will cut down some of my later part. Okay. I have something on the past climate. I'll go through that quickly. Okay.
I request that further questions you can ask him by mail or later.
Yeah, let me tell you that major problem we all know is use of cloud. And I like this nice graphics I got some, I forget from there. Unfortunately, the color is not right. So the key point about cloud represented model is there are two parts, the macrophysics and microphysics. And the macrophysics is where the models are not done well. But as you saw from all the results, as the resolution goes up, the macrophysics will be taken care of. The model will handle that. But microphysics, as already pointed out by everybody, is where we'll have a nightmare because aerosols affect microphysics. Okay. As a matter of fact, I must tell you, I read one account, I don't have the reference, where somebody introduced a bacteria in a GCM. Okay. Why? Because bacteria supposedly affects the hygroscopic nature of the aerosol. So somebody is trying to bring in biology and bacteria, but I don't know much more about that. Okay, so various things are there. To me, the most difficult problem today we are facing is the slot particle size and depends on the microphysics, which will not be solved by going to high resolution. Okay, so as summarized, I could tell you, short term, you're doing very well. Medium term is getting better. Extended range, 15 days looks promising, but this is getting to be tough. Beyond a month, so far, no model got it right. Okay, there's a repeat. Yeah, I want to give you one example of the forecast here, where you can see that this is the All India forecast in green, this is observation. So up to about 5 days is not bad, then it starts deviating. And same thing with cyclone forecast. It has improved a lot in the last 10 years. And that's why we are able to reduce the mortality due to cyclones. Okay, both landfall error and track error is very good. Yeah, and this showing how the first, second, third, and fourth pentides, how the correlation keeps going down. Okay, and I just want to give one example of the seasonal forecast last year's. You can see how the various things they forecast, they got about half right. Okay, All India, they got it right. They didn't get June and July correctly. They were very bad in August, completely wrong. And but August, September, they managed to get it right. Cancellation of errors. Then different parts of India, two parts they got it right, two parts they got it wrong. So this is the state of the field right now. One cannot criticize anyone. This is the way the subject is. Okay. Now, I want to briefly look at inter and decadal variation of the monsoon. I just want you to remember a very interesting point about the monsoon. You look at the monsoon, where is the variance of the internal variation is, the maximum is in 2.7 year cycle. Okay, this is based on a paper published by Iyengar and Raghu Khan. So this is the part we are not able to predict accurately. 66% of the variability lies in the 2 to 3 year mode. Okay, and that has not been still handled. The other one is the El Nino mode, that's 14%. That we have got some idea. And there are multi-decadal 10%, 2%, 4%, totally 98% is explained. Now, the reason why I'm showing you this is, I want to show one example of forecast done, ensemble mean forecast of over about 80 years. The red here is observation, ensemble mean of 6 atmospheric GCM is in black. You can see it's very poor. No signal, no capability. Okay, I'll do the same thing. I'll show you the decadal average. Same thing. I'm not anything. I just average it over 10 years. You can see that these models have some skill in decadal variation, but no skill in internal variation. Okay, so that shows this model has some good things, but also many bad things. Now, this is for the atmospheric model. But if you run a coupled model, yeah, and the reason why we know that the decadal modulation of the monsoon is due to Atlantic multi-decadal oscillation, which is observed in North Atlantic, that controls the monsoon variability on a 60-year time scale. Okay, but if you run a coupled model, there is no skill. Black is the model, red is the. So you can see that the good skill we got because we supplied the temperature with the atmospheric model, then it does well. Run a coupled model, it goes haywire. Okay. Yeah. So I have about 5-10 minutes. Okay. I'll just cover the. So I've got to say a few words about the past monsoon, because why should we study past monsoon? Okay. The reason is we have just 150 years of rain gauge data, and that period may not contain all the modes of variability. Okay. We should be alert to the fact that 150 years of data does not tell you the whole story of what could happen to the Indian monsoon. The reason why I'm saying this is because Sahel in Africa had a terrible 30 years of drought continuously from 1970 to 2000. It could create absolute mayhem in Africa, political problems and starvation. Now, India never had more than 2 consecutive droughts. Okay, so we are lucky. Whenever one drought, the next year normal, above normal. Now, people assume that this is a norm, but I'm not sure. I think when I look at longer data set to realize whether such long periods of drought can occur or not. Okay, so I'm comparing. Let's see Sahel here. 30 years of below normal rainfall. We never had that. We always had ups and downs. Okay. There are periods of very good rainfall, and then some period. So we never had a long. Okay, here somewhere here, early 1900s, there was some long period of below normal rainfall, but it was punctuated by a few good years. Okay, now the reason why you must look at the past is that based on proxy data, we know that although present day Sahara is a desert, 7,000 years ago Sahara was a savanna. It had fairly good rainfall, and a lot of archaeological and other data show that rainfall had gone up 7,000 years ago. Okay, and then it declined. Okay, now we look get the past data of monsoon only through either caves where there are these stalagmites. From there you can get the delta O18. That's one way. Then there are other ways also to extract rainfall information. Okay, and there's just some detail which I ignored. Okay, so Yadav and Ramesh have shown that delta O18 in these caves is connected to rainfall, either daily or monthly. Okay, Now, here is a comparison between, from a Chinese scale, the rainfall variation over the last 250,000 years. Okay, I want you to remember this, 250,000 years rainfall data is there. And it's compared with solar radiation variation at that latitude, 30 knot. Okay, it's remarkably close. Okay, that shows that on a long time scale, okay, not year to year, rainfall is proportional to incoming radiation. Okay, that follows from the simple model. If all the other things don't vary, S and P are proportional. Very nice result, but that's not always true. This is what Kutzbach showed about 30 years ago. There's incoming radiation variation, and these two are connected. And so we wanted to look at what happened in the last ice age, how was the monsoon and how it evolved as it came to present day. Okay. Now for that we used, and if you look at the model, the proxy data from the Bay of Bengal, it shows that during the period 0 to 10,000 years before present, the slope of solar radiation versus rainfall was 1, but the slope in the declacial between 18,000 to 10,000 was very different. Okay? So this was the puzzle we wanted to solve. Why is the relation between S and P so different in the two periods? Okay. And so we used this simulation provided by NCAR. NCAR did a wonderful job for everybody for running their model for 22,000 years. I mean, it's a remarkable achievement. You cannot do it. You don't have the resource, but they did it and put out the data on their website. Okay, anybody can use it. And I would suggest many of you want to play around with data. There's a beautiful data to look at. And not only they did run for the entire period with variations in radiation, greenhouse gases, ice sheets, water, and so on. They also did separate variation, changing one at a time. So this is very much required for understanding. For understanding, you have to look at each forcing separately to understand what's going on. So these are the various numbers. You can look at it in their website. Now here is the comparison between the model simulation in black called Trace 21K and the observation from Bay of Bengal called in one of the ice, what do you call, ocean sediments, KL26 at this location. You can see that the comparisons are not perfect, but pretty good. Okay, so clearly the rainfall was around 4 millimeters per day in that region during the last ice age, and it is now around 7 millimeters. Okay, and the model is able to capture it. So to me, that is a remarkable achievement of the model. So we wanted to use the model to understand why that is happening. For that, you need a diagnostic model. I used the diagnostic model I discussed earlier. The same model, slight difference, because this quantity is not 1 anymore. And you can see the diagnostic model reproduces the observed rainfall measure operation reasonably well. There are some deviations which I will not discuss today. This can be explained, but the rapid increase from deglaciation and the decrease after the peak is reproduced very nicely. Okay? So I'm going to use the diagnostic model to explain what's going on. And it reproduces, this was the proxy, this is the model, very good comparison. In both of them, the slope is different. Okay? And it is a repeat of that. Now, we have calculated these quantities which I talked about earlier, these quantities for, I got the wrong one, this is Bay of Bengal. Let's see, India is or not. I'm sorry, I don't have it. This is for Bay of Bengal, not for India. So we are able to show that the calculation of TGM is sensitive to how the vertical profile of mass static energy and the omega vertical velocity varies. They are not same over land and ocean. Ocean has air going very deep, while over land it is more shallow. Okay, and that alters the vertical integral. How we calculate that? So this is an example of the vertical profiles over land and over ocean. Now, what's interesting is we were able to show that in the last 10,000 years, the rainfall over India declined, rainfall of Bay of Bengal went up. Okay, so I will not have time today to discuss. Anyway, I can send you the paper. You can look at it in greater detail. So we have a complete theory based on the diagnostic model, how radiation from the sun as well as changes in greenhouse gas and ice sheets affect the surface temperature and hence affect the water vapor, also energy available, that Q net, and affect this. So we're able to explain both the variation during deglacial and Holocene. Okay, so this decline in the last 10,000 years due to radiation decline, nothing else. Okay, and so one can see that if only you depend on a variation in radiation, you cannot explain the full variation. Okay, full variation would account the large change in water vapor from the last glacial age to the present. Okay, and I think this all are this all are looking at induced simulations where only orbit is changed, only greenhouse gas changes, or only ice changes. Those are all special thing to understand what's going on. And yeah, I'll skip all that. That is not necessary. Yeah, I think this all will be. So what we showed that water vapor influences monsoon in various ways, as a greenhouse gas, as it condenses water vapor, and also is lighter than air. Remember that water vapor is a thing which is lighter than air. Whenever water vapor is there, air is more buoyant. Okay, all these alters the simulation. So this was what we completely arrived at, how radiation change affected ice, CO2, methane, whatever, and greenhouse effect. I think I'll skip all that. But I mentioned that all the products showed you so far was for a 100-year average. You look at year to year, there's lots of variation due to changes in dynamic circulation. So we looked at this 100-year average, which is okay for a 22,000-year long period. Okay. And here I want to show you that in this period, you cannot explain the rainfall variation by only S variation. S hardly varied by 7%, 100%. So we have to bring in the large change in water vapor to give the answer. Well, these are all the fine points. So I want to end with this conclusion. On time scales of very long time scale, 20,000 more, rainfall depends only on incoming radiation. Okay, that's fine. But you go to a smaller time scale, it depends both on radiation and water vapor. You go to even smaller time scale, decadal and so on, you will have what they call vertical mass static energy difference. It depends on circulation. Okay, so that's the conclusion we arrived at. And so I'm sorry I couldn't detail, but that paper is available to you. You can look at it in more detail. Okay, I think I'll skip all that and come to conclusion. Thank you.
Can I ask one? Hello.
Yeah.
So you started with that the monsoon can be thought of as some manifestation of this meridional movement of ITCZ. I mean, is this fully accepted in the sense of like as a causal effect, as you were mentioning, or is it still at the correlation stage?
Which one?
The meridional movement of ITCZ. Can that be thought of as a cause of the monsoon?
Meridional movement of ITCZ is documented. There is no doubt about that. Okay.
Okay. But is it like a correlation or a causation in some sense?
What?
He's asking, is it causal? Is ITCZ causal for rainfall?
Yes. I mean, ITCZ, so ITCZ is defined as the east-west oriented rain band. It is a rain band definition. So rain is there by definition. Okay. ITCZ is the region where rainfall exceeds evaporation and is zonally oriented, east-west.
Right.
So that is by definition. It does rain because if it doesn't rain, it's not an ITCZ.
Lokahit?
I can't hear you. Sorry. Can you remove mask? Because with mask, I have a great difficulty. Yeah.
So you showed us the plot of outgoing radiation between, the Indian subcontinent
Right.
and say North Africa, the Saharan region.
Net rate, not outgoing, net.
Okay.
That is S into 1 minus alpha minus overall. Net radiation. Very important. That's not outgoing.
Okay. So I just wanted to know how much this is affected by the land use patterns and things like that.
Yes,
For
it's
example,
affected.
if you imagine
Land use pattern determines how much is reflected. Suppose you have a desert, you reflect more. If you have forest, it reflects less. Of course, it reflects affected. Yeah.
So a scenario where like
I'll repeat. Sahara presently has a high albedo. Okay, but Sahara 7,000 years ago had vegetation. It had a low albedo. It had more rainfall. So land use has a huge impact on. Definitely.
and
As a matter,
so
let me tell you this point. People always talk about CO2. As far as India is concerned, any rainfall change in India is much more influenced by land use change than CO2 any day.
and so would it be a correct statement to say desertification causes more desertification and vice versa?
Yes, as a matter of fact, Charney, the great meteorologist, said this 40 years ago. He argued that as you start to remove the vegetation, albedo increases, net radiation goes down. So he had a full cycle description. And if you want to know more about it, there's a beautiful paper by Neelan on the vegetation feedback in Sahara. He has a model and he explains the whole thing, how you start from vegetation, all your no vegetation, how the thing goes. Okay, it's well documented.
Last question.
So, Professor Srinivasan, first of all, let me thank you for this beautiful talk as well. I have a very vague and general question, but just to ask you, in your view, are the global climate models missing something essential vis-a-vis the monsoons? That is,
that I think Saravanan and everybody has pointed out. What they're missing is the correct modeling of clouds. That's very clear.
of the clouds.
100%.
Okay.
But I'm convinced that part is partly solved when you go to high resolution, except for aerosol. Aerosol is a total nightmare. I don't know what they're going to do because it affects microphysics. It is at a scale where a model cannot do much, right? You can go to any resolution model, but your microphysics, you have to put in from observation. There is no shortcut to that.
So that was going to be my second part, which is, so now let's suppose we go to 7 kilometers or something resolution, we then still miss out the aerosols, as you were saying.
Yes.
But could we...
a great improvement. What I'm trying to say is the present poor simulation is partly due to parameterization. That will go away. Okay? But still, there will be one problem remaining. We don't know how much it is. Even today, we are not clear about exactly, because aerosol does two things. It affects the radiation budget. It affects the cloud. Okay? They go in the opposite direction. In most models, I have seen those two cancelling out. I don't know whether your experience is the same. But those two effects, I don't know why, they go in the opposite direction. So if you're lucky, it cancels out, you're okay.
I see. Okay.
But it's a tough problem. Microphysics of the cloud is very hard problem.
I see. But is there a sense in which you mentioned, I wanted to ask you, that the aerosols become less important after the advent of monsoons? So maybe with a 7 kilometer resolution, can we hope at least to improve the prediction to a month or 2 months from the year?
Yeah, I expect that. That all of us are expecting that once you go to, I think I'm hoping that you'll see in the next few years, because the 7 kilometer model, you cannot run it for 100 years, which I would like to run as an academic. But running for 3 months is not a problem. I'm sure they may do it next year. They're all working on it. Okay? So they may start doing it one or 2 years as soon as the computer is ready, because that's not a big jump. Okay? So I think that part will handle. So you will see, like we saw a good improvement in the weather forecast because of assimilation. You will see a good improvement in a month and higher forecast in the next few years, definitely. But there's a question mark about aerosols still. Because no model, even now, I think no model has dust in it. That's the problem.
Thank you.
Okay, if there's no more questions, let's thank Professor JS again.